Welcome to Sleepy Science Channel number 1. Have you ever wondered just how unlikely life on Earth was? How many factors needed to be just right for it to ever even be possible? Tonight is all about settling in, letting the day soften at the edges, and easing into a quiet story that drifts across cosmic time. This is a gentle place to settle your mind, a quiet corner to breathe a little slower, to let your thoughts unfold in their own easy rhythm. Before we drift into tonight's journey, I want to thank you for listening, wherever you may be. When you have a moment, I'd love to know where in the world this little video has reached you. It's always comforting to imagine this peaceful nighttime community stretched across continents, each of us sharing the same calm curiosity in the dark. If these slow, quiet explorations of science bring you a sense of rest, feel free to give the video a like and consider subscribing. And if you're already part of this cozy circle, thank you. You're the reason these gentle journeys can continue. Do tap the notifications bell as well, so you never miss the next late-night wander through the universe. This video is designed to help you rest, but with a topic like this one, there is always the tiny risk that it might actually keep you awake for a moment or two. If it does, at least you might drift off a little wiser than you were before. Tonight, we're exploring something gentle, yet enormous in scale. The story of how you came to exist at all. Not just how humanity appeared, but how the entire universe, across more than 13 billion years, arranged its conditions so precisely that a thinking, breathing person like you could be here to listen to this. It is a journey through fragile chances and narrow windows of possibility, each one balancing on the next. So before you let your eyes grow heavy, settle in and get comfortable. Have you ever wondered just how close the universe came to never creating anyone at all? The path to human life is a long chain of quiet miracles, each depending on the last, each more unlikely than it first appears. The beginning of this journey stretches back to a time when there were no stars, no planets, and certainly no place for anything alive to take shape. The early universe was a wild and brilliant storm of energy. And yet, within that storm were the faint seeds of the chemistry that would one day allow life to appear. This introduction is here to guide you gently into that story, one step at a time. Everything that exists today, from oceans to trees to your own heartbeat, can trace its origins to ancient events that happened long before Earth was even a thought in the cosmos. Tiny changes in temperature, delicate balances between expansion and collapse, the quiet gathering of matter in the darkness, all slowly shaped the world. You know, life did not simply arrive. It depended on extraordinary timing, impossible coincidences, and long stretches of calm between moments of catastrophe. This is a story told slowly, not to overwhelm, but to show just how many fragile threads had to weave together for a single person to exist. It is a reminder that your life is not just the result of biology or ancestry, but of the entire universe holding steady through countless turning points. As the journey begins, imagine following a single thread backward, all the way through billions of years, past stars forming and dying, past worlds colliding and cooling, until you reach the place where possibility itself first flickered into existence. And from there, the improbable path to you begins. The beginning of the universe was not quiet, and it certainly was not gentle. Yet everything that exists now depends on how those first moments unfolded. Imagine a time before time meant anything, when space itself had not stretched wide enough to be recognizable, when everything that would one day become galaxies and oceans and living beings was pressed into a tiny, searing blur of energy and potential. It is hard to picture a place without shape, but that is where the story begins. In a moment so brief that it barely counts as a moment at all, as the universe rushed outward in its earliest breath, it was unimaginably hot, a brightness beyond anything stars could ever hope to match. This heat mattered because it dictated what could survive. When everything is that energetic, nothing stays still long enough to hold together. The early universe was a sea of particles flashing in and out of existence, colliding, ricocheting, and dissolving back into light. But as the expansion continued, that intense heat began to fade. Not quickly, but steadily, like a long exhale. The balance between expansion and gravity played the first crucial role. A balance so delicate that if either side had taken even the tiniest step too far, nothing familiar would have formed. If expansion had roared ahead slightly faster, matter would have been scattered too thin across space, never gathering into anything more complex than a vague mist of particles. A universe that expands too quickly cannot hold on to things. It becomes a place where nothing lingers long enough to take shape. On the other hand, if gravity had been the stronger partner, if that pull inward had dominated, everything would have collapsed back into itself almost immediately, crushing any chance for structure to form. In that version of reality, the universe would have walked out as quickly as it began, a brief flare with no room for stars to breathe or planets to coalesce. But our universe threaded the impossible middle path. Expansion relaxed just enough to slow the chaos. Gravity held on just enough to coax matter together. It is difficult to express how fine this balance was. A tiny shift either way, a change so small that it would barely register on any human scale, and the universe would be empty, or it would be gone. Instead, it opened into a space where matter could eventually settle, cool, and gather. As temperatures fell across the newborn universe, particles that had been flying freely began to link together. Protons and neutrons found each other first, forming the simplest atomic nuclei. It did not happen evenly. Some regions were a little denser than others, a little more crowded, and in those slightly fuller pockets, matter clumped together more readily. These tiny irregularities would later become the seeds of galaxies, but at this early stage, they were just flexes of unevenness floating in a growing cosmic sea. Even then, atoms could not form properly until the universe cooled further. The early heat kept tearing them apart. It took hundreds of thousands of years of quiet expansion before electrons could finally settle into stable orbits around the nuclei waiting for them. When that happened, something remarkable occurred. The universe, once blazing and opaque, suddenly became transparent. Light that had been trapped in the dense early plasma was finally free to travel across space. That ancient light still moves through the universe today, stretched into a faint microwave glow that fills the sky. It is a quiet reminder that the earliest chapters of cosmic history never fully disappear. Once atoms formed, the universe entered a kind of calm that had never existed before. It was still expanding, still cooling, but the frantic violence of its first moments had softened. Hydrogen was everywhere, sprinkled through space in vast, diffuse clouds. A smaller amount of helium drifted alongside it. These two simple elements would eventually become the building blocks of stars. But at this stage, they were spread so thinly that nothing dramatic happened for a very long time. Space was enormous, and these new atoms had all the room in the world to drift. Yet even in this quiet structure was quietly emerging. Gravity, patient and persistent, began tugging on the slightly denser patches of gas. Slowly, over millions of years, those regions drew in more and more material. The process was gentle at first, almost unnoticeable. But gravity is relentless, and if it finds the faintest advantage, it will use it. Clumps grew heavier, and as they grew heavier, they pulled in surrounding gas even faster. These subtle gatherings mark the earlier stages of what would one day become stars. If the early universe had been just a fraction smoother, if matter had been distributed more evenly, nothing would have clumped at all. A perfectly uniform universe would have been calm, but too calm for stars to ever be born. Without tiny imperfections, gravity would have nothing to gather, nothing to hold on to. But the early universe wasn't flawless, and that gentle unevenness became a gift. Little clumps of matter formed, small pockets where gravity could begin its quiet work. Over long, drifting ages, these pockets grew denser and warmer, slowly tightening into themselves. And then, deep in those warm centers, something new awakened. Not the fiery heat of the beginning, but a softer, steady rising, just enough for hydrogen to fuse. Light blossomed out of the darkness, and the very first stars began to shine. It was a second dawn, not the birth of the universe, but the birth of the structures that would one day shape everything within it. The rarity of a universe like ours lies in how many delicate conditions had to fall gently into place for this quiet miracle to unfold. It needed a particular rate of expansion, a particular strength of gravity, specific ratios of matter, and tiny initial imperfections. Change any of these by even a breath, and the universe becomes a place without stars, or without planets, or without the chemistry that leads to life. A universe can exist without being life-friendly. Most probably do. The fact that ours happened to land in this narrow band of stability is extraordinary. In that early darkness, with new stars lighting up like small lanterns, the universe transformed from a storm into a landscape. Gravity sculpted clouds of hydrogen into glowing spheres. Light began to thread its way through space. The first galaxies swirled into shape, each one a vast gathering of billions of stars. And within those galaxies were the quiet, patient processes that would eventually create heavier elements, worlds, and all the conditions needed for existence to unfold. This chapter of the story is not just about whether the universe began, but how it began. It is about the balance between forces that do not negotiate, about the behavior of matter under unimaginable conditions, about the long cooling breath that allowed atoms to settle into place. It is the foundation of everything else that follows, because without this precise beginning, nothing familiar could have arrived. The universe had to begin just right for stars to form, for planets to take shape, and for life to find a home. And in this vast, ancient darkness, long before Earth existed, the first threads of your improbable path were quietly being woven. Long before Earth formed, before oceans settled or air gathered, the universe needed stars to act as its great alchemists. The first stars that lit up the darkness were enormous, short-lived giants, brilliant enough to change the entire chemistry of the cosmos, but far too unstable to serve as homes for life. They were loud, bright, impatient creatures, burning through their fuel in just a few million years. But despite their brief existence, they played one of the most important roles in your story. Because inside their cause, they were forging the elements life would one day require. For a long time, hydrogen and helium were all the universe had to offer. Beautiful in their simplicity, but not enough. Life needs carbon, it needs oxygen, it needs nitrogen, calcium, iron, phosphorus, and many others. These are not primitive materials. They are made in places of staggering heat and pressure, places where the weight of a star's own gravity squeezes atoms together until new kinds of matter bloom into existence. Deep inside those early stars, fusion slowly stitched small atoms into larger ones, like letters forming words that the universe had never spoken before. But stars do not just create heavy elements. They must also give them away. And this is where timing becomes everything. A star cannot release its creations gently. It must wait until the end of its life, when its fuel runs low and its core collapses. That collapse triggers a chain of events so intense that it tears the star apart in a brilliant explosion. A supernova is violent, but it is also one of the most generous events the universe has ever known. It scatters the star's elements across space, sending carbon, oxygen, silicon, and iron drifting outward in great expanding shells of debris. Those elements mix into the surrounding clouds of gas, enriching them, preparing them for the next generation of stars and planets. But the timing of these explosions is not simple. If the earliest stars had lived too briefly or died too frequently, the galaxy would have been flooded with radiation and shock waves too chaotic for later structures to form. If they had lived too long, the galaxy would have remained poor in the elements needed for complexity. There is a quiet tension in the way stars live and die. They must burn hot enough to create heavy elements, but not so violently that they tear apart the regions that future stars need to form. They must explode often enough to enrich the galaxy, but not so often that they sterilize it. The earliest giant stars handled the heavy lifting, seeding space with the first round of complex elements. But they were only the first step. The next generation of stars formed from clouds that had absorbed these new ingredients. And those stars lived longer, burned more steadily, and created yet more elements in their cores. When they died, they added to the growing pool of cosmic material. It took multiple cycles of birth, life, and destruction to create the chemical richness that our planet would eventually inherit. Imagine it like layers of paint on a vast cosmic canvas. Each generation added new colors, new textures, new possibilities. The universe began almost monochrome, bright but simple. Over time, with each stellar life and death, it became more detailed, more varied, more capable of producing worlds with oceans, atmospheres, and the chemistry needed for biology. Without these repeated cycles, the universe would still be a cold, thin spread of hydrogen. Nothing solid, nothing heavy, nothing alive. But even within this long cosmic process, the timing remained delicate. If too many stars died all at once in a region, the shock waves would rip apart the very clouds of gas that future stars needed. The galaxy would become turbulent, chaotic, and unkind to growth. If too few stars died, the enrichment would stall, leaving future systems without the materials for planets like Earth. Thankfully, our corner of the galaxy experienced a rhythm that was neither too fast nor too slow. Waves of star formation rose and fell in gentle cycles, sometimes quiet, sometimes busy, but never extreme enough to upset the balance. Some of the elements needed for life require even more unusual processes. Gold and platinum, for example, appear mostly during rare, powerful events like neutron star collisions. These are among the most spectacular events in the universe, flinging out heavy metals in luminous sprays. The fact that Earth contains these materials means that somewhere in the galaxy's ancient past, these extraordinary events happened at just the right distances and times for their debris to drift into the cloud that would eventually become the Sun, the planets, and you. As the galaxy aged, its chemistry deepened. Clouds of enriched gas gathered in its spiral arms, forming great swirls where new stars lit up and old stars faded. Over billions of years, this gentle recycling shaped the environment from which our solar system eventually emerged. When the Sun formed, it was not a first-generation star born from pure hydrogen. It came from material that had been through many stellar lifetimes. Material that had been cooked, shattered, sifted, and scattered. Every atom in your body carries a history far older than the Earth itself. And here is the quiet miracle. The Sun formed at exactly the right stage in this cosmic recycling. Early enough that the galaxy was not yet crowded with destructive events, but late enough that the material it formed from was rich with the elements life would need. Had the Sun been born several billion years earlier, the Earth might have been short on essential elements. Had it arrived several billion years later, the spiral arms of the galaxy might have become too disturbed by later generations of stars, too scattered or too chaotic. Everything depended on cycles that unfolded slowly over unimaginable spans of time, each one adding a little more complexity to the universe. The heavy elements forged inside stars are the same elements that make up the air you breathe, the blood that flows through your body, and the minerals that shape every landscape on Earth. You are quite literally the dust of stars that lived and died long before the Sun drew its first breath. In a universe where many regions remain barren, where some corners never gathered enough material for planets, and others were torn apart by constant explosions, our galaxy found a particularly gentle rhythm. Stars lived long enough to enrich it. They died far enough apart to avoid widespread devastation, and they repeated this pattern billions of times, quietly shaping the chemistry that would one day give rise to life. By the time it was our solar system's turn to form, the galaxy had already done its quiet, patient work. Generations of stars had lived their luminous lives and then faded, returning their elements to space in soft, drifting waves. Each cycle left behind more richness, more complexity, more possibility than the one before. Without this long history of cosmic recycling, Earth would have been nothing more than a dry sphere of hydrogen. And the long, delicate path that led to you would have ended before it ever began. But the universe moved at its own unhurried pace. It cooled, it gathered, it created, it burst apart, and then it began again. In those repeating rhythms, stars became the quiet authors of the chemistry that shapes every living thing, including the one resting here tonight, listening to their ancient story. They lit their fires, forged their elements, returned them to space, and passed on the baton to the next generation. Through their patient work, the building blocks of life found their way into the clouds that would one day form the sun and its planets. Your story does not begin on Earth. It does not even begin in the solar system. It begins in the hearts of ancient stars that lived and died at exactly the right moments, leaving behind the ingredients you now carry in your own body. Most stars in the universe are not like the sun. In fact, if you were able to drift quietly through the galaxy, weaving between the countless points of light scattered through the dark, you would notice very quickly that the sun does not fit in with the majority. Most stars are far smaller, cooler, and dimmer. They burn with a faint red glow that barely reaches beyond the systems they anchor. These small stars are known for their frugality, stretching their fuel across trillions of years. But their long lives often come with temperaments that are anything but gentle. They flare violently, sending storms of radiation blasting across their surroundings. Their temperamental behavior makes life extremely difficult for any world that might orbit close enough to be warm. The sun stands apart. It belongs to a class of stars that sits comfortably between extremes, a kind of golden middle ground. Not too big, not too small, not too faint, not too bright. These stars are often called yellow dwarfs. And despite the slightly unimpressive name, they're among the universe's most precious. They make up only a small fraction of all stars, perhaps 1 in 10, depending on how you count. In the crowded population of the cosmos, where the tiniest red stars outnumber all others by a huge margin, stars like the sun are rare jewels. What makes them special is not only their size, but their temperament. The sun is steady, predictable. It shines with a brightness that has changed only gradually across billions of years. This quiet consistency is vital. Life, especially complex life, needs stability. Temperature swings, long dark periods, sudden flashes of radiation, or rapid changes in light output can eliminate the possibility of oceans, atmospheres, and the chemistry required for living things to endure. The sun, for reasons that come down to mass, composition, and magnetic behavior, gives off a steady, warm, and remarkably even glow. If it had been slightly larger, it would have burned hotter and faster, racing through its fuel in just a few 100 million years. That sounds like a long time in human terms, but in cosmic terms, it is hardly enough for a planet to cool, develop oceans, and begin forming life. If the sun had been smaller, its habitable zone would have been so close that Earth would need to sit uncomfortably near its surface. In that scenario, Earth would be battered by intense flares and bursts of ultraviolet light, as smaller stars are notorious for their unpredictable tempers. A calm, steady star is incredibly valuable, and the sun achieves this balance almost effortlessly. One of the quiet wonders of the sun is how stable it has remained over the 4.5 billion years of Earth's history. Stars change as they age. Their luminosity increases. Their surface behavior shifts. Their magnetic fields dance through cycles that can affect the worlds orbiting them. Yet the sun has moved through these changes slowly enough that Earth's climate has had time to adjust rather than collapse. Early in its life, the sun was dimmer, casting a fainter glow over the young Earth. Yet the planet compensated through atmospheric chemistry and volcanic activity that trapped more heat. As the sun brightened, Earth gradually altered its balance in return, releasing heat-trapping gases more sparingly. Neither partner moved too quickly, and their quiet collaboration maintained the stability life would eventually require. Another crucial piece of the puzzle rests in how the sun behaves in ultraviolet wavelengths. Ultraviolet light can be energetic enough to break apart molecules and damage early life. Too much of it can sterilize a planet's surface. Smaller stars often produce huge ultraviolet flares, bright enough to strip atmospheres and destroy organic compounds. Larger stars bathe their systems in harsh radiation that would make life difficult even at great distances. The sun sits in a comforting window. It produces enough ultraviolet to drive important chemical reactions in Earth's atmosphere, but not enough to scorch it bare. This delicate balance may be one of the reasons Earth was able to develop both protective ozone and the early biochemistry needed for life. Beyond the sun's own behavior lies another often overlooked piece of the puzzle: the neighborhood where it lives. Not all regions of the galaxy are equally peaceful. Some are crowded with enormous stars that explode frequently. Some are filled with dense clouds of gas and dust, where star formation is so active that whole clusters light up at once, producing intense radiation fields. There are also regions with wandering black holes, neutron stars in gravitational disturbances that can destabilize orbits. The Sun, by contrast, resides in a quiet suburb of the Milky Way, not too close to the bustling galactic center, where stars crowd together and radiation levels soar, not too far into the outer fringe, where material for planet formation becomes scarce. It sits in a broad, calm spiral arm, where stars are spaced far enough apart to avoid constant interactions, yet close enough to draw from ancient cycles of enriched material. This peaceful location gave Earth the opportunity to form undisturbed and remain undisturbed for billions of years. Even the Sun's birth environment appears to have been unusually kind. Many stars form in clusters that eventually drift apart, but in their early years, those clusters can be dangerous. Massive stars blasting out ultraviolet radiation can strip young planets of their atmospheres before they even form. Supernova can detonate nearby, flooding young planetary systems with harmful particles. Somehow, the Sun was born in a cluster that dispersed quickly enough to avoid these dangers. It slipped away from the crowd before any large neighboring stars reached the ends of their lives. As the Sun matured, it continued to show the kind of behavior that life relies on. Its energy output increased slowly. Its surface storms remained moderate, and its magnetic cycles, while occasionally dramatic, were never intense enough to render Earth inhospitable. Quiet stars allow time. They allow continents to drift, oceans to form, climates to stabilize, and life to evolve from the simplest cells into forests, coral reefs, and eventually conscious beings who can look back on the universe and wonder how it all began. In a galaxy filled with stars that flare violently or fade too quickly, stars that wander near supernova or sit too close to black holes, stars that never shine brightly enough for planets to warm, our Sun holds a rare and precious middle ground. It provided just the right amount of light, just the right amount of stability, and just the right amount of ultraviolet energy. It lived in a neighborhood spacious enough for peace, yet rich enough in history to offer the materials Earth needed. The improbability of human life is built into this chapter of the story too. If the Sun had been slightly different, if it had been born in the wrong place, with the wrong mass, the wrong brightness, or the wrong temperament, Earth would have been a barren world drifting through space. There would be no trees reaching toward the sky, no oceans breathing clouds into the air, no living creatures watching the seasons change. The chain that leads to you would have snapped before it even began. Instead, an uncommon star formed. A star steady enough to warm its planets gently. A star bright enough to sustain life, but calm enough to avoid destroying it. A star with just the right mass, just the right chemistry, and just the right placement in the galaxy. A rare star, shining quietly in a quiet corner of the Milky Way, waiting patiently for life to grow around it. When the sun was still young and the solar system was settling into shape, countless fragments of rock and ice were circling in broad, shifting paths. Out of this swirling cloud, planets began to grow, gathering material one collision at a time. But only one of these planets found itself in a place where the warmth of the sun and the chill of deep space balanced in just the right way. This narrow, fragile region is often called the Goldilocks zone, a band of space where temperatures can allow liquid water to persist on a planet's surface. Too close to the sun, and every drop of water would lift into the sky as steam. Too far, and it would lock itself into ice. Earth settled into a narrow strip of cosmic real estate, so delicate, so exact, that even the slightest shift would have turned it into an entirely different world. This distance is far more precise than we often imagine. Nudge Earth a little closer, and the oceans would have boiled away, leaving behind a scorched, silent landscape like Venus. A world where heat becomes a tightening trap, growing stronger with time. Move Earth just a little farther out, and the planet would slip into deep freeze, an icy sphere more like the frozen moons of the outer solar system than a home for life. The window for liquid water is narrow, especially for a star like the Sun. Earth just happened to fall into that delicate band where sunlight delivers enough warmth to keep water fluid, but not enough to strip it away. In that narrow balance, oceans formed and stayed, holding the chemistry that would one day give rise to life. But distance alone was not enough. A planet's temperature depends not only on how far it sits from its star, but also on how it moves, how it tilts, and how evenly it distributes the heat it receives. Earth does not orbit the Sun in a perfect circle. Its path is slightly stretched, just enough to change the world's distance from the Sun across the year. If that stretch had been more extreme, Earth would swing dangerously between scorching summers and deep freeze winters, a kind of seasonal chaos that could stop complex ecosystems from settling. Instead, Earth's orbit is gentle, just uneven enough to give the planet mild variations, the kind that creates seasons rather than catastrophes. Rotation plays a role too. Earth spins at a pace that distributes warmth around the globe, reducing extremes between day and night. Turn the planet much faster, and winds would scream around the world at unimaginable speeds. Turn it much slower, and one side would bake under unending sunlight, while the other chilled beneath eternal night. Earth rotates at a rhythm that keeps the temperature steady enough for life, stirring the atmosphere slowly, mixing heat between dark and light in a way that encourages balance. Then there is the tilt. Earth leans just over 23 degrees away from upright, a modest angle that shapes the seasons. Without this tilt, the planet would be locked into everlasting sameness, with the equator blistering and the poles freezing, and life might have emerged only in narrow bands where conditions were tolerable. If the tilt were far greater, the seasons would swing wildly, leaving half the world frozen and half overheated at different times of the year. Instead, Earth enjoys a tilt that gives variety without instability, subtle shifts in sunlight that guide ecosystems gently, rather than overwhelming them. These layers of balance allowed Earth to maintain long-term surface water, one of the rarest planetary conditions in the universe. Water is everywhere as vapor, ice, or fleeting droplets in the atmospheres of distant worlds. But liquid water on a safe, open surface is astonishingly uncommon. Many planets hold water locked as ice deep beneath their crusts, far from sunlight. Others had water once but lost it to radiation or runaway greenhouse effects. Even among the known exoplanets orbiting distant stars, candidates with lasting oceans are extremely few. Most worlds swing too hot or too cold. Earth sits in a tiny, careful gap between those extremes. Solar energy alone cannot guarantee a steady climate. Earth's atmosphere traps some heat, but not too much. It reflects some sunlight, but not too much. It allows water to evaporate, form clouds, fall as rain, and return to the oceans in a circulation that maintains stability. Early in Earth's history, the sun was dimmer, and yet Earth managed to stay warm enough. Later, as the sun brightened, Earth did not overheat. This slow exchange between star and planet relied on countless small adjustments in atmospheric chemistry and geological activity. Volcanoes released heat-trapping gases when the sun was faint. Weathering on land removed those gases gradually as the sun strengthened. Without this quiet dialogue between the planet and the star, Earth could have veered into climates too extreme for early life to survive. This balance extended to how Earth formed and held on to its atmosphere. The planet's gravity had to be strong enough to keep an atmosphere from drifting into space, yet not so strong that volcanoes smothered the world with thick layers of gas that trapped too much heat. A planet even slightly smaller might have lost its air long ago. A planet slightly larger might have been wrapped in suffocating clouds. Earth found a middle point that allowed air to circulate, water to stay liquid, and sunlight to warm the surface without overwhelming it. Even the sun's energy output, stable as it is, fluctuates in subtle ways. Even the smallest variations ripple softly through the solar system, but Earth's climate cushions these shifts with remarkable grace. Its oceans breathe slowly, absorbing heat and releasing it over long, steady intervals, smoothing out temperature changes that might otherwise arrive too suddenly. Without these vast blue reservoirs, the planet would swing wildly between scorching heat and bitter cold. With them, Earth moves in a gentler rhythm, one that life can follow, one that feels almost like a heartbeat. True habitability is not just about short-term comfort. Across millions and even billions of years, Earth has wandered through cycles that could have ended its capacity to support life, if not for the quiet, stabilizing feedbacks woven into the planet's systems. These deep, patient balances have guided the planet through danger again and again, allowing life to continue its long, unfolding story. Ice reflects sunlight, cooling the Earth. But if too much ice spreads, the planet cools faster. Volcanoes release gases that warm the atmosphere. But if too much heat gathers, weathering removes those gases. These natural counterweights act like quiet guardians against climate extremes. Without them, Earth might have frozen solid or overheated, ending the long story of life before it truly began. When scientists search for planets around distant stars, they look for those Earth-like conditions: worlds with oceans, balanced atmospheres, mild orbits, and steady temperatures. Yet, even in the growing catalog of exoplanets, most promising candidates fall short in one way or another. Some orbit stars that flare frequently. Some are tidally locked, showing only one face to their star. Some have atmospheres too thick or too thin. Earth, by contrast, feels almost improbably fortunate. It orbits the right kind of star at the right distance with the right tilt, spin, and atmospheric composition. Every factor that keeps Earth habitable has changed over time. but each change has been gradual enough for life to adapt. The planet has avoided rapid, catastrophic shifts that might have erased entire biospheres. Oceans did not boil. Ice did not swallow continents forever. The atmosphere did not vanish. Instead, Earth's climate hovered within a narrow, life-friendly corridor, allowing evolution to take root and expand. The Goldilocks zone is more than just a distance. It is a long-term partnership between a planet as its star, a quiet collaboration where temperature, chemistry, motion, and sunlight work together. Earth happened to form in this rare zone. It managed to hold onto its water. It maintained its atmosphere. It kept its climate stable enough for billions of years. And through these quiet balances, through these narrow windows, life found room to grow. When you look at the Earth today, with its blue oceans, drifting clouds, and landscapes shifting gently from season to season, it is easy to forget how fragile that balance truly is. The planet lives in a narrow band of possibility, a sliver of space where water can flow and life can take shape. Most worlds in the universe never know such stability. Most never hold seas. Most never get the chance to breathe. Earth did. And that narrow, improbable placing in the Goldilocks zone became one of the first and most essential steps on the long path that eventually led to you. When people look at the moon in the night sky, it is easy to think of it as a simple companion drifting quietly above the world, with no particular purpose beyond offering a soft glow and a familiar shape. But the moon is far more than a decorative fixture. It is one of the most important reasons Earth remained a stable, life-supporting world for billions of years. In the long chain of improbabilities that eventually led to you existing, the moon is one of the most surprising. Most planets, even large ones, do not have moons anywhere near the size of Earth's. Ours is enormous compared to the planet it orbits, large enough to influence Earth's behavior in profound and subtle ways. If you were to shrink Earth and the moon down to the size of 2 spheres you could hold in your hands, the moon would not be a tiny marble next to a large globe. It would feel more like a smaller but still substantial sphere, one that clearly contributes to the system rather than merely tagging along. Among rocky planets, this arrangement is extremely rare. Mars has 2 tiny moons shaped more like potatoes than worlds, and Mercury and Venus have none at all. Having such a large moon is unusual, and having one that formed in the way ours did is even more remarkable. The moon's size matters for many reasons, but one of the most important is the stabilization of Earth's axial tilt. Earth spins like a slightly tilted top, leaning just over 23 degrees. This tilt gives us seasons, influences climate patterns, and affects how heat and light spread across the planet. Without the moon, Earth's tilt would not remain steady. Gravitational tugs from other planets, especially Jupiter, would slowly pull and nudge Earth into chaotic shifts. Over long stretches of time, the tilt could wander dramatically, swinging between near upright and extreme angles. These wild changes would create unpredictable climates, some plunging the poles into long scorching periods, and others locking vast regions into unending winters. With the moon in place, Earth's tilt is anchored. The moon's gravitational pull keeps Earth's axis steady, holding the planet in a stable orientation that changes only very slowly. This stability is not something we think about during our daily lives, but it is essential. A predictable tilt allows Earth's climate to unfold in slow, manageable rhythms. Seasons follow one another in a pattern that life can depend on. Without that consistency, habitats would shift too rapidly and violently for complex ecosystems to survive. Entire climate zones might appear and vanish within the span of a few thousand years. With the moon's reassuring tug, Earth avoids such chaos and maintains a gentler, more predictable world. The moon's influence extends to the tides, those quiet, rhythmic rises and falls of the oceans that shape coastlines and ecosystems around the world. The tides are driven mainly by the moon's gravity pulling on Earth's oceans, stretching them slightly and causing water to bulge toward and away from the moon. These tides are not just pleasant coastal phenomena. They act as a kind of planetary heartbeat, moving enormous amounts of water in regular, dependable cycles. This motion does far more than shift the shoreline. Tides stir the oceans, mixing warm surface water with cooler layers below. This mixing redistributes heat and nutrients, helping marine life thrive and transporting essential elements across vast distances. In Earth's early oceans, tidal mixing may have played a crucial role in spreading the chemicals needed for life to emerge. Shallow pools were replenished regularly, concentrating molecules and promoting reactions that eventually gave rise to the first living cells. Without strong tides, the early oceans might have remained too stagnant for these processes to unfold with such richness. Furthermore, the tides shape coastlines into dynamic environments where life can flourish. Estuaries, tidal flats, mangroves, and salt marshes all depend on the daily pulse of the ocean. These shifting boundary regions often contain some of the greatest diversity of life on the planet, acting as nurseries for countless species. Over Earth's history, such tidal zones may have served as stepping stones for life moving from water to land, offering sheltered, nutrient-rich environments where early organisms could experiment with new ways of living. The moon's gravitational pull also affects Earth's rotation itself. Long ago, in the deep past of our planet, Earth spun much faster than it does today. A day may have lasted only 6 hours. Over billions of years, the moon's pull slowed Earth's rotation, lengthening the day and shaping the world's climate. A slower rotation smooths out temperature differences between day and night, calming winds and creating a more stable environment for life. While this effect happens gradually, it has a long-term influence on how ecosystems evolve. All these stabilizing effects on tilt, climate, tides, and rotation depend on the moon's mass, and the way the moon acquired that mass is one of the most extraordinary events in Earth's history. According to the leading scientific explanation, the moon formed when a Mars-sized object collided with the young Earth. The impact was unimaginably violent, blasting enormous amounts of rock and molten material into orbit around the planet. Over time, this debris gathered into a glowing ring that slowly coalesced into the moon we know today. This giant impact origin is rare. Collisions were common in the early solar system, but the specific conditions required to form a large, stabilizing moon are extremely unlikely. The colliding object had to hit at just the right angle and speed. Too fast, and Earth would have been destroyed. Too slow or too direct, and the impactor would have merged with Earth without leaving enough debris to form a moon. The materials flung into orbit had to cool, gather, and bind together before drifting off into space. And the resulting moon had to settle into the right distance, not too close and not too far, to stabilize Earth's tilt and produce strong tides. The fact that this sequence of events happened exactly as it did is astonishing. Earth could so easily have become a world without a moon, wobbling unpredictably, swinging between climate extremes, and lacking the regular tidal pulses that nurtured early life. Instead, the moon formed with the perfect mass and position to act as a guardian of planetary stability. Over the billions of years that followed, the moon remained a steady presence in Earth's sky. As continents drifted and oceans formed, as life emerged and diversified, as climate shifted in slow, gentle rhythms, the moon continued to anchor the planet's behavior. It is not an exaggeration to say that without the moon, Earth might never have developed stable environments long enough for complex life to evolve. Forests, coral reefs, and even the familiar patterns of wind and weather all depend on the quiet influence of that pale sphere above. Today, when the moon rises, it does more than illuminate the landscape with silvery light. It shines as a reminder that Earth's story includes improbable events, ancient collisions, and delicate balances. The moon's presence is a testament to the narrow path our planet followed, a path that allowed life not only to begin, but to flourish. And in the long chain of unlikely moments that led to you, the creation of a uniquely stabilizing moon was one of the most important of all. In the earliest days of the solar system, Earth was not the blue world we know now. It was a dry, scorched landscape, a newborn planet built from rock, metal, and heat. The young sun blasted intense radiation across a chaotic cloud of debris, and temperatures near Earth's orbit were far too high for water to survive in liquid or even solid form. Any ice that drifted too close evaporated immediately, and any moisture trapped inside early rock was baked out into space. The Earth that formed in this environment was bone dry, without oceans, rivers, rain, or even the faintest trace of mist. Yet life, as far as we understand it, needs water, not a little water, not scattered droplets. It needs oceans, lakes, currents, and cycles. It needs liquid water that can act as a solvent, a mixer, a carrier, and a cradle. Without water, Earth would have remained a barren, rust-cold sphere of dust and volcanic plains. So the question becomes, if Earth formed dry, where did all the water come from? The answer lies in the chaotic outer regions of the young solar system, where icy bodies drifted like frozen passengers waiting for their turn to be sent inward. Beyond the orbit of the young Earth, temperatures fell sharply. In those distant zones, ice could survive. Comets formed there, along with small icy worlds rich in frozen water. Over time, gravitational interactions between the forming planets sent many of these icy bodies hurtling inward toward the Sun. Some were flung out entirely, lost to the dark. Others crossed paths with Earth. The young Earth was constantly bombarded by fragments of rock and ice, countless impacts shaping its surface. Among these incoming travelers were water-rich bodies from the colder outer regions. Every time one collided with Earth, it delivered a tiny amount of water. At first, these deliveries would have seemed insignificant compared to the planet's vast, steaming surface. But the bombardment continued for millions of years, each impact adding a little more to the supply. Slowly, drop by drop, the ingredients for oceans were gathered, even as the planet's crust cooled and hardened. This process was chaotic, dangerous, and violently unpredictable. Sometimes, enormous impacts would boil away shallow pools of early water in minutes. Other times, they delivered fresh ice that melted into new lakes and seas. Over time, Earth's temperature fell enough that water could stay in place instead of evaporating into space. But even then, the balance was fragile. If too much water had arrived, Earth could have become a world entirely covered in deep ocean, with no land masses breaking the surface. A planet like that might still support life, but it would struggle to produce the diversity of environments that led to complex organisms, land plants, or eventually intelligent beings. On the other hand, if too little water had been delivered, Earth would have remained dry, with scattered pockets of moisture evaporating as quickly as they formed. Water needs to gather into long-lasting reservoirs before it can drive the chemistry of life. Too little water, and the planet becomes Mars, cold, empty, and silent. Too much, and the world becomes a global ocean with no cycles of weathering, no continents, and no place for life to evolve beyond microscopic drifters. The narrow range of water that allows Earth's rich variety of life sits in a small band between these two extremes. Yet out of the violent ballet of early impacts, Earth somehow received just enough water, not too much, not too little. The deliveries came in waves. Some came from comets, made mostly of ice, others from asteroids containing water locked inside minerals. Many struck too fast, their water lost to the heated atmosphere. Others hit gently enough that their icy cargo melted and pulled in sheltered regions. As Earth's crust cooled further, deep cracks and fractures opened across its surface, forming basins and valleys that collected the falling water. In the beginning, those ancient basins held only scattered, quiet pools of water. Rain could not yet fall. Earth's early atmosphere was still thick with volcanic breath, too heavy and too warm for weather to find its rhythm. But as the air slowly thinned and cooled, something extraordinary happened. Water vapor gathered into clouds, and for the very first time in Earth's long history, rain touched the ground. Not soft showers, but sweeping torrents. Storms rolled across the young planet, filling craters, swelling newborn oceans, and carrying minerals from raw stone into the waiting sea. That first rainfall was not a single moment. It was the beginning of a cycle that still moves through the world today. Water rose from the warm oceans, drifted upward, cooled, and fell again as rain, shaping continents with every pass. Rivers carved their first pathways through untouched land. Oceans deepened. The earliest coastlines appeared like gentle outlines on a newborn world. The natural systems that now support every ecosystem on Earth had their beginnings in those ancient downpours. The gradual arrival of water also influenced the planet's temperature. Water is excellent at absorbing and releasing heat, smoothing out the sharp temperature spikes of day and night. As Earth's oceans grew, they acted as stabilizers, preventing violent swings that could have wiped out early chemical pathways. A world with oceans cools more slowly, warms more gently, and maintains habitable conditions more reliably. This stability allowed fragile molecules to assemble, interact, and ultimately form the first living systems. Earth's water did not arrive in one moment. It came through countless tiny decisions made by gravity, by impacts, by chemistry, and by the slow evolution of the solar system. Each icy fragment that struck Earth added a little to the balance, and each addition nudged the planet toward becoming something more than a dry rock. It took millions of years, but eventually enough water had pulled across the surface to fill oceans thousands of meters deep. Those oceans became the cradle of life. They sheltered molecules from ultraviolet radiation. They concentrated chemicals in tidal pools. They cushioned early organisms from the harsh conditions above. They made Earth blue, reflective, and vibrant. Without that long period of chaotic delivery, the world would have remained barren. From a distance, Earth looks calm now, a world wrapped in water and drifting peacefully around the sun. But the serenity is the result of an ancient, turbulent process that delivered water in just the right amounts at just the right times. And without that delicate balance, without those countless icy messengers from the outer solar system, the improbable path to life, and eventually to you, would never have begun. Water did not simply appear, it arrived through cosmic chaos. Survived intense heat and collected slowly in the cooling bowls of a young planet. It came from far beyond Earth's birthplace and settled here long enough for life to take root. And once life began, water carried it forward, shaping every chapter that followed. The early Earth was not a calm or gentle place. It was a world still cooling from its birth, battered by rocks the size of mountains, and reshaped constantly by forces beneath its surface. The oceans that had slowly gathered were never guaranteed to stay. More than once, they were nearly boiled away. More than once, the planet came close to losing the fragile ingredients it needed for life. And yet somehow, through chaos that stretched across millions of years, Earth kept recovering. Not perfectly, not quickly, but just enough, just in time, again. And again, one of the most dramatic threats came from giant impacts. Even after Earth had settled into something resembling its modern shape, space was still filled with leftover fragments. From planetary formation, some were small enough to burn up in the sky as harmless streaks of light. Others were enormous, drifting through the inner solar system like silent boulders. Every so often, one of them crossed Earth's path. When that happened, the result could be catastrophic. A large enough impact could release more energy than all the world's volcanoes combined, heating the surface so intensely that oceans could vaporize in minutes. There were times when this nearly happened. A single collision had the potential to turn Earth into a global steam bath, a place where any developing chemistry would be scrubbed away. These events did not simply splash water aside. They heated entire oceans, evaporating them into thick clouds that wrapped the planet in steam. If too much water had been lost to space before the atmosphere cooled, Earth could have remained dry forever, with no chance for life to form. But the planet cooled just quickly enough. Water condensed, rain fell, oceans returned. The Earth, still bruised and scarred, found its balance again. Volcanism was another force that tested Earth repeatedly. The early crust was thin and restless. Beneath it, molten rock surged and churned, seeking weak points where it could break through. Volcanoes were not rare peaks dotting the landscape. They were everywhere. Entire regions split open in floods of lava, and enormous eruptions blanketed the sky with ash and gases. These eruptions were powerful enough to remake the atmosphere again and again. Every time Earth lost air to space or had its chemistry altered by impacts, volcanoes pumped out new gases, carbon dioxide, nitrogen, water vapor, rebuilding the envelope that wrapped the planet. But volcanic activity could also push Earth to the edge. Too much carbon dioxide turned the atmosphere into a thick, suffocating blanket. Too little, and the planet risked freezing. The balance was delicate, shifting constantly as volcanoes erupted and then fell silent. There were periods when volcanic gases warmed the planet just enough, and other periods when their absence chilled it dangerously. But never did the scales tip so far that Earth became permanently uninhabitable. Somehow, despite the violence, the climate always returned to a range where water could remain liquid and chemical reactions could continue. As if impacts and volcanism were not enough, Earth also faced near-sterilization events that came from the planet's own atmosphere. When the early sun was still young, it produced stronger ultraviolet radiation than it does today. Without an ozone layer to block that radiation, the surface of the planet was exposed to destructive bursts of energy. Lightning storms crackled across the sky, splitting molecules apart. Steam from hot oceans rose into the air and broke apart under ultraviolet light, with hydrogen escaping into space. There were times when this process nearly stripped away Earth's water entirely. If the atmosphere had lost too much hydrogen, the oceans would have shrunk, turning Earth into a world of drying basins and widening deserts long before life could gain a foothold. Yet, as temperatures cooled, the atmosphere thickened in just the right way. Water vapor condensed, clouds formed. The planet shielded itself. Volcanic gases filled in the missing pieces of the atmosphere. Slowly, a fragile but workable balance returned. Even after life began, the young microbial world faced repeated challenges. Global cooling episodes nearly froze the oceans solid. Warming episodes threatened to turn shallow seas into inhospitable brine. Impacts continued, though less frequently, each one threatening to disrupt the fragile chemistry unfolding in the water. But life endured. Sometimes just barely, sometimes in forms so simple that they could hide from the worst conditions. But it endured. There is something remarkable in the way Earth repeatedly recovered. Each recovery was not a guarantee. It was a narrow escape. Sometimes water boiled away, but not completely. Sometimes cooling froze the world, but not entirely. Sometimes volcanic heat scorched the surface, but left hidden pools untouched. Every catastrophe had the potential to erase progress, to start the clock over again, or to end the story altogether. But in the long run, Earth stayed within the slender margin that allowed both water and chemistry to persist. A world in Earth's position did not need to collapse dramatically to fail. It only had to tip slightly too far for slightly too long. The difference between a planet with shallow seas nurturing early life and a planet locked in permanent ice can be surprisingly small. A few degrees of temperature, a shift in atmospheric gases, one unlucky impact, one prolonged volcanic surge. Yet Earth drifted through these dangers with just enough resilience and just enough luck. The planet absorbed shocks without falling permanently into ruin. One of the reasons these recoveries were possible lies in the diversity of Earth's environments. Even when the surface became extreme, sheltered places remained. Deep ocean vents continued to release heat and chemical nutrients. Caverns beneath the surface offered pockets of relative stability.
Small basins of warm water could reform quickly after cooling events. Life does not need perfection. It needs pockets of possibility, and Earth somehow maintained those pockets through every trial. As the planet aged, the catastrophes became less frequent. The solar system grew calmer, impact slowed, the crust thickened, allowing volcanism to focus into fewer but more predictable regions. The atmosphere developed layers and complexities that helped regulate temperature. Over time, Earth transitioned from a world barely clinging to balance into one that could support long-term stability. Still, those early catastrophes left their mark. They shaped the landscapes we see today and influenced the chemistry of the oceans.
They stirred the atmosphere, redistributed minerals, and tested life's resilience. Without those stresses, life on Earth might have taken a very different path, possibly a slower one, possibly a path that never led to complex organisms. But the challenges forced life to adapt, to innovate, and to find ways of enduring that would later give rise to diversity. The margin between survival and collapse was thin. Yet Earth walked that line with surprising steadiness. Through boiling oceans, frozen horizons, volcanic tempests, and skies thick with steam and ash, the planet remained somehow just suitable enough. It was in this fragile balance, maintained again and again across millions of years, that the improbable path to life continued. Out of destruction came opportunity. Out of chaos came stability. And out of those early storms came a planet ready to nurture the next stages of evolution, carrying the story one step closer to you. Life's beginning on Earth was not a single spark, not a moment where everything clicked into place at once, but a long sequence of delicate steps unfolding in narrow windows of opportunity. The planet had water, warmth, minerals, and the right kinds of chemical gradients. But even with all those pieces, the leap from simple molecules to self-sustaining life was astonishingly unlikely. The ingredients were abundant, but the recipe was fragile. Countless attempts at chemistry must have risen and faded long before anything resembling a living cell appeared. For life to emerge, the right molecules had to meet in the right places under the right conditions, and then somehow persist long enough to improve upon themselves. Organic molecules had been drifting through Earth's oceans for millions of years before anything organized into something more structured. These molecules were constantly forming, breaking apart, mixing, and rearranging. They came from volcanic gases, lightning strikes, reactions at mineral surfaces, and even fragments delivered by meteorites, rich in carbon compounds. Everywhere on the young Earth, chemistry was happening. But chemistry becoming biology required something more. A way for molecules to assemble into arrangements that could hold together and make copies of themselves. This delicate transition, the shift from simple chemistry to the first hints of life, needed a place where molecules could gather and linger, rather than being swept endlessly through young, restless oceans. That is why many scientists turn their attention to quiet, hidden places, like hydrothermal vents or shallow tidal pools. Deep beneath the surface of the early sea, hydrothermal vents breathed warm, mineral-rich water into the darkness, rising from deep within the crust like ancient underwater springs. Around these vents, steep chemical gradients formed, tiny worlds of contrast, full of energy and possibility. Materials built natural scaffolds in the surrounding rock, creating pockets and channels where wandering molecules could become trapped for a moment, held close just long enough for rare reactions to unfold. Here, warmth was gentle and constant. The chemistry was rich, layered, and endlessly renewing. And in a world still harsh and unstable, these sheltered environments offered something precious, a small corner where conditions stayed steady enough for the earliest steps toward life to quietly begin. Tidal pools offered another possibility.
These shallow basins along ancient coastlines filled and emptied as the tides moved in and out, concentrating molecules as water evaporated in the sunlight. A tidal pool could begin the day diluted and end it as a thick, syrupy mix of organic compounds. When the tide returned, it stirred everything together, creating new combinations.
Day after day, cycle after cycle, these pools acted like nature's laboratories, messy, imperfect, but full of potential. Both environments shared a key feature. They offered pockets of stability within a world that was otherwise unpredictable. Early life needed those pockets. Organic molecules cannot organize into anything meaningful if they are constantly scattered, overheated, or washed away. They need time to assemble, time to interact, time to form patterns that persist long enough to evolve. Whether in the deep oceans or the shifting edges of tide-washed shores, these quiet corners of Earth provided that rare opportunity. The leap from molecules to early cells required one of the most improbable steps in all of biology: self-replication. Having a structure is not enough. For life to begin, something needs to be able to make a rough copy of itself. Not perfect, early replication almost certainly produced endless mistakes, but good enough to pass on its general shape.
Those mistakes over generations would eventually lead to improvements. But getting to that first act of copying was incredibly difficult. Many chemical systems could form briefly, but they fell apart before replicating. Others could copy themselves in simple ways, but not reliably. Only a few reached the threshold where replication could outpace decay. Some hypotheses suggest that early self-replicating molecules were similar to forms of RNA, a versatile molecule capable of both storing information and helping reactions occur. Others suggest that simpler systems existed first using mineral surfaces as templates. Whatever the mechanism, it had to arise in conditions that were neither too harsh nor too calm, where chemistry unfolded rapidly but without being destroyed instantly. Even after the first self-replicating systems appeared, they faced countless challenges. They had no protection, no membranes, no stable environments.
A shift in temperature, a surge in acidity, a change in salinity, or a collision with another chemical system could destroy them. These fragile chains of molecules existed at the mercy of their surroundings. For any lineage to survive, it had to find a way to shield itself from the chaos. That is likely where the first primitive membranes emerged. Simple bubbles formed from fatty molecules that trapped mixtures of chemicals inside. These early proto-ells, tiny spheres floating in the water, were imperfect, leaky, and unstable. But they provided just enough protection for the chemistry inside them to persist a little longer than before. With time, the molecules inside those early bubbles became more organized. Some improved the ability to replicate. Some helped gather nutrients from the environment. Others helped stabilize the membrane. In a world full of chance, these tiny advantages mattered. The earliest proto-ells did not have goals. They simply survived, because their internal chemistry lasted longer than others. The ones that fell apart did not leave descendants. The ones that held together passed their quirks forward. Countless lineages must have flickered in and out of existence during this era. Some may have copied themselves a few times and then vanished. Others might have spread across small regions of the ocean, only to be wiped out by changing conditions. The vast majority of early experiments in biology left no trace. Only a single lineage survived through all the chaos. Every living thing on Earth today, from bacteria to whales to humans,
descends from that successful lineage, the one that managed to endure where countless others failed. How did that one lineage succeed? Perhaps it found a slightly more sheltered environment. Perhaps it developed a molecular mechanism that made copying more reliable. Perhaps it incorporated a particular molecule that made its membranes more stable.
We may never know the fine details because the earliest stages of life left no fossils. But what is clear is that survival depended on timing, environment, and luck. The chemistry that became life had to emerge during a narrow window when Earth was stable enough for self-replication, wet enough for chemistry, and cool enough for membranes to form. Once that lineage crossed the threshold into sustained replication, life became a persistent feature of Earth. It could adapt. It could spread. It could survive the planet's shifting conditions in ways that non-living chemistry could not. But the path to that point was steep, fragile, and full of near misses. The emergence of life was not guaranteed, even on a world so rich in water and minerals. It was a sequence of improbable steps, each relying on the one before, each demanding conditions that might easily have failed. And yet, through a combination of environmental pockets, chemical innovation, and sheer persistence, life established itself. From scattered molecules drifting in ancient oceans came the first whisper of biology. And from that whisper came everything else that would follow. The improbable path to you began not with perfect conditions, but with fragile chemistry that somehow endured long enough to take the first breath of life. The earliest cells on Earth were simple, small, and self-contained, tiny bubbles of chemistry drifting through ancient oceans. For millions of years, they survived on little more than luck, sunlight, minerals, and modest reactions that allowed them to gather energy and copy themselves. They were remarkable in their persistence, but they were limited. Each one lived alone, with no special tools, no internal compartments, and no partnerships to help it do anything more than survive. Complex was not yet part of the picture, but slowly, over vast stretches of time, early cells began to invent it. One of the most important steps came from a moment of unlikely cooperation. At some point in the deep past, one kind of simple cell engulfed another. This was not unusual. Cells frequently encountered each other, bumped into one another, and sometimes swallowed each other. But in this particular case, the swallowed cell did not break apart and dissolve. Instead, it survived inside its host. Rather than being digested, it became a partner. This strange coexistence would eventually give rise to one of the most powerful innovations in the history of life. The engulfed cell turned out to be excellent at handling energy. It could take in simple molecules and use oxygen to produce far more energy than its host could ever manage alone. Over time, these energetic inner cells became permanent residents. They stripped away some of their own machinery and transferred some of their genes to the host. Eventually, they became what we now call mitochondria, the power sources found in almost every complex organism. In plants and algae, a similar partnership happened again, this time with cells capable of photosynthesis, becoming the chloroplasts that allow green life to capture sunlight. These mergers were monumental. They allowed early cells to grow larger, to hold more internal machinery, and to organize themselves in new ways. They unlocked the ability to support more complicated structures because the energy available per cell increased dramatically. With more energy came more possibilities. Cells could afford to build protective membranes, store molecules, and repair themselves.
They could invest in strategies that took time to pay off. They could survive in new environments. The invention of internal symbiosis opened the door to complexity. But these innovations did not appear overnight. Life spent billions of years in the single-celled stage, slowly refining the partnerships and improvements that made complexity possible. These early cells experimented with different shapes, different ways of feeding, different ways of protecting themselves. Some developed simple skeletons made of minerals. Others created internal scaffolding that allowed them to move or change shape. Some began to sense their surroundings with greater precision. All these small steps accumulated, each one building on those that came before. Eventually, a remarkable shift began to happen. Cells started gathering in groups. At first, these clusters were temporary, forming for convenience and then drifting apart. But soon, some cells began sticking together permanently. This was the first step toward multicellular life. By cooperating, cells could share resources, divide tasks, and specialize. One cell might focus on gathering nutrients, while another focused on movement. Another might take on the role of defense. Cooperation allowed these early organisms to achieve things that no single cell could manage alone. The earliest multicellular organisms were simple. They resembled sheets, filaments, or hollow spheres of cells, each performing similar tasks but benefiting from being part of a group. Over long periods of time, some of these organisms evolved more defined roles. Certain cells took charge of reproduction. Others formed protective outer layers. Some became contractile, helping the organism move or adjust its shape. The first multicellular creatures on Earth were neither fast nor intelligent, but they were pioneers. They represented a new level of biological organization. This cooperation, however, required new systems to keep everything coordinated. Cells had to communicate with each other, sending tiny signals across short distances. They needed ways to stick together without breaking apart. They needed rules to make sure each cell divided at the right time in the right place and did not grow out of control. These systems formed slowly, guided by trial, error, and the pressure to survive. Life invented hormones, chemical gradients, adhesion molecules, and the first forms of cellular signaling, each one allowing organisms to grow larger and more intricate. In these early stages, the rise of complexity often came with setbacks. Some multicellular experiments failed to hold together. Others grew too slowly or lacked the ability to compete with faster, simpler cells. There were long stretches of time where it seemed as though simplicity might always dominate. But the advantages of cooperation eventually outweighed the costs. Multicellular organisms could explore new environments, survive harsher conditions, and grow into shapes that helped them gather more energy than their single-celled ancestors. One of the keys to this rise was the development of internal structure. Cells invented ways to build fibers and networks within their bodies, forming early skeletons. These structures allowed simpler organisms to maintain shape, to change direction, and to move more effectively. Some cells developed cia, tiny hierarchy extensions that beat rhythmically to move water or propel the organism. Others developed flagella that acted like tiny motors. With these early biological tools, the first multicellular organisms began to move through their ancient worlds with a quiet kind of grace. Some glided, some swam. Some drifted or curled and crawled across soft sediments. Even within a single cell, complexity was unfolding like a slow, delicate bloom. Membranes folded inward to create tiny, sheltered rooms where different reactions could unfold safely. Molecules traveled along invisible pathways, carried like precious cargo on miniature conveyor belts. Energy was gathered, stored, and released with growing accuracy, little sparks of order in an otherwise wild world. Sensitivity to light, warmth, chemicals, and motion began as faint whispers, barely detectable, but enough to guide these early beings toward opportunity and away from danger. These subtle skills formed the quiet foundation that later life would refine and expand. As ages drifted by, more intricate shapes appeared. Early multicellular organisms experimented with new forms, branches reaching outward, filaments stretching thin, flat sheets waving gently in the currents. Some settled firmly on rock and sand, anchoring themselves in place, forming soft carpets and layered mats that slowly, steadily transformed the chemistry around them. Others drifted freely, catching currents and feeding on floating particles. The oceans became laboratories of experimentation, with countless new variations appearing and vanishing. Many left no trace, but a few found stable solutions that could persist across generations. The transition from simple cells to complex life was not quick. It was one of the longest phases in Earth's history, spanning billions of years. But each innovation added a little more depth to the living world. Each partnership, each structural change, each new kind of cellular cooperation expanded what life could do. Slowly, complexity shifted from being an experiment to being a reliable way of surviving. What makes this chapter extraordinary is how unlikely it was. Mergers between cells could have failed. Cooperative groups could have fallen apart. Energy innovations could have proved too costly. Yet through persistence, chance, and gradual refinement, life invented complexity, layer by fragile layer. And once it did, the world could never go back to being simple again. From those early experiments grew forests, reefs, insects, animals, and eventually beings capable of thought and memory. The leap from simple cells to complex organisms was one of the greatest turning points in the improbable path that eventually led to you. Life on Earth has never traveled in a straight, peaceful line. It has flourished, collapsed, reinvented itself, and begun again more times than the surface of our calm, modern planet might suggest. Across deep time, Earth has endured at least 5 great mass extinctions, each one a period when environmental upheaval swept across the globe with such intensity that most living species vanished. These were not gentle transitions. They were sharp, sudden breaks, moments when the world changed faster than almost anything could adapt. And yet each time, life survived. Not the same life, not the same ecosystems, but enough life to rebuild the future from the remnants that remained. The first of these great extinction events occurred long before animals walked on land, at a time when life existed mainly in the oceans. The world then looked utterly alien. Sea creatures drifted through waters, teeming with forms that now feel almost imaginary. Bizarre, soft-bodied organisms shaped like fronds, discs, and ribbons. But the calm appearance of those early seas hit a fragile balance. A shift in climate pushed oxygen levels downward, and vast stretches of the ocean became hostile. Many species died out quietly, leaving only those able to withstand low oxygen conditions. The world lost much of its early diversity. Yet a few small, simple, resilient organisms endured. From them, new ecosystems slowly emerged, setting the stage for future evolution. Millions of years later, the oceans underwent another profound transformation when early animals began experimenting with hard shells and active movement.
This was a time of explosive biodiversity, a period when life explored countless new forms. But it did not last. Climate swings and changes in ocean chemistry struck again, stripping oxygen from large regions of the sea. Many early animal groups vanished. Yet once more, small survivors persisted at the edges. Creatures that could tolerate low oxygen, that could burrow into sediments, or that simply lived in places untouched by the turmoil. When conditions eventually improved, evolution restarted, moving in directions it would never have taken without the reset. One of the most devastating extinction events arrived at the end of the Purian period, often called the Great Dying. It was an extinction so severe that it nearly erased complex life altogether. Volcanic eruptions on a scale beyond anything seen before or since flooded the atmosphere with carbon dioxide, triggering global warming, ocean acidification, and the collapse of countless ecosystems. Over 90% of marine species disappeared, along with vast numbers of land animals and plants. Forests vanished, oceans turned stagnant. The world became a harsh, inhospitable place. And yet, not everything died. Small animals living in burrows, hardy plants with simple structures, and microorganisms capable of surviving in hostile environments endured. These survivors occupied niches emptied by the catastrophe, and slowly, patiently, evolution began again. The ecosystem that followed were different from anything that came before. New species rose to fill the open spaces. New forms of life emerged, each one shaped by the world left behind. Without the Great Dying, the dominant animals of the next era would have evolved very differently. Another mass extinction struck at the end of the Triassic period. At that time, the supercontinent Pangaea was beginning to break apart. Volcanic activity surged once again. Atmospheric chemistry changed rapidly, pushing global temperatures into chaotic swings. Many species that had begun to rebuild after the previous extinction were lost. But again, small, adaptable species survived. Among them were the early relatives of the creatures that would eventually dominate the next era, the dinosaurs. Dinosaurs rose not because they pushed others aside, but because previous extinctions cleared the stage for them. When life restarts, it does not rebuild the same way. It experiments, explores new body shapes, new behaviors, new ways of living. Dinosaurs filled empty ecosystems with astonishing variety. They grew into towering plant eaters, nimble runners, enormous predators, and creatures that soared through ancient skies. For more than 150 million years, dinosaurs ruled a world transformed by earlier catastrophes. But their reign, too, was destined to end. The fifth great extinction arrived suddenly, caused by an asteroid that struck Earth with unimaginable force. The impact released energy greater than billions of atomic bombs, sending dust and debris high into the atmosphere, blocking sunlight for months. The world plunged into darkness. Plants died. Food chains collapsed. Fires burned across continents. Most dinosaurs, along with many marine species and countless smaller organisms, perished. And yet, once more, life refused to disappear entirely. Small mammals survived, sheltered in burrows and forests. Birds, descendants of feathered dinosaurs, made it through. Plants left seeds able to wait out the darkness. When sunlight returned and the skies cleared, evolution began rebuilding from these survivors. Without the extinction of the dinosaurs, mammals might never have become dominant. Humans might never have appeared. The asteroid that ended one chapter opened the doorway to another. Each mass extinction came with a pattern, a global disaster,
the collapse of established ecosystems, and the survival of species that were small, adaptable, and often overlooked. These survivors carried the future on their shoulders, shaping what life would become. Evolution did not simply bounce back. It changed direction. It explored new possibilities. What had once been common vanished. What had once been rare became abundant. Entire worlds of potential opened up only because earlier ones had ended. Mass extinctions remind us that the history of life is not a steady climb toward complexity. It is a winding path full of dead ends, narrow escapes, and abrupt transformations. Each catastrophe reshaped the world. Each one influenced which species thrived, which traits succeeded, and which lineages continued. The diversity we see today, including humans, exists because of the unpredictable ways life responded to these global resets. The improbable path to you passes through every one of those ancient crises.
At each turning point, the ancestors of your ancestors survived. They endured heat waves, ice ages, darkness, volcanic winters, shifting continents, and collapsing food webs. They were small, often humble creatures, unnoticed in their time, but crucial to the story of the future. Their survival was not guaranteed. It depended on chance, resilience, and the delicate interplay between life and environment. Without those survivors, those tiny, determined beings who outlasted catastrophe, the world would be unrecognizable. Forests, birds, mammals, and humans might never have existed. The mass extinctions that seem so destructive from afar were also opportunities for renewal, allowing life to evolve in ways that would have been impossible otherwise. Through all the turmoil life endured, it restarted. It reshaped itself. And with every reset, the story grew richer, leading eventually to the fragile, improbable moment in which you now exist. The story of humanity is often imagined as a steady rise, a gradual unfolding from early ancestors into the modern world. But the truth is far more fragile. Our lineage did not expand smoothly across time. It narrowed, faltered, and almost disappeared more than once. The path that leads to modern humans is not a wide highway, but a thin, winding thread that survived by chance and resilience through a series of genetic bottlenecks, climate crises, migrations, and extinctions. At many points in deep time, our ancestors came alarmingly close to vanishing entirely. One of the defining features of human evolution is how often our population shrank to extremely small numbers. Genetic research suggests that early human population sometimes dwindled to just a few thousand individuals and possibly even fewer. Such bottlenecks strip away genetic diversity, reducing a population's ability to adapt and making it vulnerable to disease, climate shifts, and random chance.
Yet our ancestors survived them, carrying forward a limited but persistent set of traits that would eventually spread across the world. Climate played a major role in these narrowings. Earth's environment during the rise of early humans was anything but stable. Repeated ice ages advanced and retreated, reshaping landscapes, drying out forests, expanding deserts, and forcing animals and people to migrate. Regions that were lush and green became barren. Water sources shifted. Food sources collapsed. The hominin species that lived through these periods had to be both flexible and lucky. Sometimes populations split into isolated groups as shifting climates pushed them to new refuges. Some of those groups eventually died out, leaving no descendants. Others endured in pockets of stability, small valleys, lake shores, mountain edges, where conditions were harsh but survivable. Migration was not a choice made with foresight, it was a necessity.
Early humans and their ancestors followed moving herds, shifting vegetation and dwindling rivers. They crossed plains that later became deserts and climbed highlands that later grew treacherously cold. Some groups encountered new climates successfully. Others reached regions where they could not survive. Human evolution is full of migrations that ended in failure, forgotten pathways terminating in extinction. The fact that one lineage kept moving, kept adapting, and kept surviving is an extraordinary stroke of continuity amid constant upheaval. The human family tree once had many branches. We were never alone in the world. For most of our history, several human species coexisted. Neanderthals lived across Europe and Western Asia, strong and well adapted to cold climates. Denisovans thrived in regions of Asia we still barely understand. Other more mysterious species, like Homo floresiensis and Homoni, occupied unique niches. These ancient humans were not primitive steps on a simple ladder. They were complete in their own way, fully formed beings with their own rhythms, their own strengths, their own quiet cultures shaped by landscapes long vanished. And yet, over the slow turning of ages, they disappeared. Some slipped away as climates changed around them, unable to adjust to the cooling or warming of their homelands. Others faced growing pressure from roaming bands of Homo sapiens, whose expanding presence reshaped the world. A few populations may have dwindled gently, their numbers thinning over thousands of years until only silence remained. Some of these ancient groups met ours and mixed with us for a brief moment in time, leaving behind delicate strands of their DNA still carried by certain people today. But as distinct species, they faded. What remains is the echo of their existence. Ghosts woven into the human story, unseen companions who shaped our path, even though their faces, their voices, and their names have been carried away by time. This disappearance of other human species marks one of the narrowest points in our evolutionary history. Had Neanderthals survived in greater numbers, or Denisovans expanded further, or some unknown lineage thrived in changing climate, the world today might contain multiple human species living side by side. Instead, only one remained. Our lineage, for reasons that still inspire scientific debate, persisted when others could not. Perhaps it was adaptability, perhaps it was broader diets, more flexible social structures, or more efficient communication. Perhaps it was simply chance. Evolution does not guarantee success to the strongest or the smartest. It favors those who happen to endure. Even within our own species, survival was not smooth. There were key moments when our ancestors faced collapse. Tens of thousands of years ago, a massive volcanic eruption, known as the Toba event, may have plunged much of the world into a volcanic winter. Ash darkened skies, temperatures dropped, ecosystems struggled. Some theories suggest this event temporarily shrank human populations to critically low numbers. Whether the impact was as severe as once thought remains debated. But what is clear is that our ancestors survived a period when the world changed with terrifying speed. There were other bottlenecks, some tied to droughts, others to ice expansions, others to the challenges of spreading into unfamiliar lands. Each narrowing stripped away possibilities. Each one reduced the human family tree to a smaller group of survivors. At each turn, our lineage persisted only because those survivors found water, shelter, food, and one another in moments when the world grew brutally unforgiving. The fragility of this lineage becomes clearer when considering how close we came to sharing the planet with other human species indefinitely. Our survival was not guaranteed.
it was one of many outcomes. The disappearance of our cousins meant that every human alive today descends from a single remaining branch. That single branch carries echoes of past bottlenecks in its genetic memory. We are less genetically diverse than many animals with far smaller populations. This narrowness tells the story of how often our species contracted, how often we nearly failed, and how astonishing it is that modern humans number in the billions today. The key survival moments of early humans were rarely dramatic in the way stories often portray. They were built from small advantages layered over time. Cooperation in harsh climates, the ability to share food, the capacity to learn and teach, the instinct to migrate rather than remain in dying landscapes. These quiet strengths mattered as much as any physical trait. They allowed small groups to hold on through crises that erased others. When the world warmed after long ice ages, human populations expanded again. When climate stabilized, migration routes opened. When new tools and strategies emerged, they spread across groups. Each recovery widened the path again, but only temporarily. Another bottleneck would come, and the lineage would narrow once more. This pattern repeated again and again, shaping the DNA of every person alive today. The improbable path to you includes all these narrowings. It includes the ancestors who survived droughts that lasted centuries, who crossed deserts that swallowed countless lives, who endured cold periods that destroyed entire ecosystems. It includes those who learned to use fire, who shared food in times of scarcity, who crossed mountains and rivers and coastlines seeking habitable ground. It includes the small bands that held on when neighboring groups disappeared forever. Humanity's existence today is not the result of a smooth or inevitable progression. It is the result of countless fragile survivals. A lineage that narrowed repeatedly but never snapped. A single surviving branch that carried the torch through deep time. And every person alive traces their origins back through those narrow passages, through moments where survival balanced on a thin edge, through ancestors who endured hardships beyond imagining. The fact that the human line persisted at all is one of the most remarkable steps in the improbable journey that led, eventually, to you. For almost all of Earth's history, the planet's climate swung wildly between extremes. Ice ages deep enough to freeze continents for millions of years. Greenhouse periods so hot that crocodiles swam in what would one day become the Arctic. Volcanic winters, scorching droughts, sudden warmings, abrupt coolings. These were the rhythms that shaped the world long before humans appeared. Through all this, life survived, adapted, and evolved. But civilization, with its fragile dependence on predictable patterns, could never have taken root in such volatility. For cities to rise, for farming to flourish, for human communities to grow and settle, the planet first needed to enter an unusually quiet stretch of time. And remarkably, it did. Roughly 12,000 years ago, Earth shifted into a climate period known as the Holocene, a span marked by extraordinary stability. Temperatures stopped swinging violently. Ice sheets retreated and stayed relatively still. The chaotic shifts that had defined the past slowed into gentle oscillations. Seasons became predictable. Rainfall patterns settled. For the first time in the long history of the planet, Earth's climate offered a window of calm long enough for humans to stop roaming and start planning for the future. Before this period, our ancestors had survived through mobility and resilience. They moved with the seasons, following migrating herds or shifting vegetation. They adapted to glacial cold and sudden thaws, but they could not predict the climate well enough to plant crops confidently or store food over long periods. Farming requires trust. Trust that spring will arrive roughly when expected, that rainfall will not vanish for decades, that winter will not arrive early and destroy a year's efforts. In a world of abrupt climate upheavals, that trust was impossible. But as the Holocene began, something changed. Temperatures stabilized within a narrow band. Annual cycles became consistent. This predictability created a new kind of opportunity. Groups of humans discovered that seeds scattered intentionally would grow in the same place next year. Small plots became gardens. Gardens became fields. Fields became the basis for settled communities. Agriculture took root independently in several regions around the world, an indication of just how profoundly the new climate stability transformed human potential. Predictable seasons shaped everything about early civilization. With regular rainfall patterns, people could irrigate crops. With reliable warmth, they could plan harvest cycles. With steady conditions, they could store grain through the winter, confident that the next growing season would not shift dramatically. This allowed populations to grow without the constant need to migrate or hunt across vast territories. Villages formed, surpluses developed, specializations emerged. Some people farmed, others crafted tools, others built structures. Over time, these villages expanded into cities. But it was not only climate that stabilized. Earth's geology entered a relatively quiet phase too. Large-scale volcanic eruptions became less frequent. The crust settled into slow continental drift instead of rapid, catastrophic shifts. Earthquakes still occurred, but vast rifting events that reshaped oceans and continents had long passed. Without massive geological upheaval, human structures could persist across generations. Irrigation canals could be maintained. Roads could be built. Settlements could remain in place long enough to evolve into complex societies. The atmosphere also behaved with an unusual gentleness during this period. Greenhouse gases fluctuated, but not with the violent swings of the distant past. Storm patterns stabilized enough for people to build homes near rivers or coasts, with some expectation of long-term safety. Wind patterns allowed early sailors to explore and trade. Clouds formed in predictable rhythms across monsoon regions. All these atmospheric consistencies created a world where long-term planning became not only possible, but increasingly effective. The environmental ban that allowed civilization was remarkably narrow. Too much heat and crops fail. Too much cold and growing seasons shorten beyond usefulness. Too much storm activity and fields wash away. Too little rainfall and communities collapse. Civilization did not emerge because humans suddenly became more intelligent or more organized. It emerged because Earth entered a rare moment where the environment aligned with the needs of a species capable of planning, learning, and cooperating. This alignment extended across continents. The Fertile Crescent developed agriculture as rivers flooded predictably each year, leaving behind rich soil. The Nile's seasonal swelling was so regular that ancient Egyptians built their calendars around it. In Asia, monsoon patterns brought regular rains that nourished rice farming for millennia. In the Americas, stable growing seasons supported maize, beans, and squash. None of this would have been possible in a world where temperatures swung dramatically every few centuries, as they often did earlier in Earth's past. Even the spread of ideas relied on stability. Trade routes could form only when landscapes remained consistent over long stretches of time. Written records developed only in societies confident they would exist long enough for the writing to matter. Technologies such as metallurgy and pottery required communities with enough surplus food to support dedicated craftspeople. None of these advances would have survived in an environment that constantly reset the game board. Civilization's rise also depended on the absence of global catastrophes. During this gentle period, Earth avoided supervolcano eruptions large enough to collapse climate systems. No massive asteroids struck the planet. Ice sheets did not surge across continents. Sea levels rose slowly enough that coastal populations could adapt.
The planet did not guarantee safety. There were droughts, floods, and local disasters, but the overall structure of the climate remained stable enough to support long-term growth. In this window of calm, humans developed languages, art, mathematics, astronomy, and government. They built monuments aligned with the stars, confident that the heavens would move predictably year after year. They carved out irrigation networks, trusting rivers to behave in familiar ways. They watched the seasons flow in cycles, shaping rituals and ceremonies around the dependable turning of the year. The rarity of this gentle period becomes clearer when looking back across Earth's history. For billions of years, the planet swung between extremes. Stability on the scale of the Holene was the exception, not the rule. Yet it arrived precisely when humans were cognitively ready to take advantage of it. If this period had begun earlier or later, or if it had never begun at all, civilization might never have emerged. The world today could be populated by scattered groups of mobile hunter-gatherers with no cities, no agriculture, no large-scale societies, and no written history. Instead, the climate settled into a calm plateau, and humanity stepped onto a path that would transform the planet. The rise of civilization, far from being inevitable, depended on a rare moment of environmental grace, a quiet pause in the turbulence of geological and atmospheric history. This was the stable stage on which human culture flourished. A gentle chapter in Earth's long story where conditions aligned just long enough for cities to rise, knowledge to accumulate, and the future to unfold. Without this brief refuge of steadiness, the improbable path to you would have taken an entirely different turn, or perhaps never have continued at all. Your existence is the result of a chain so long, so delicate, and so improbable that it stretches the imagination to even attempt to follow it. Every person alive today carries within them the echoes of countless ancestors, each one a survivor of their own fragile moment in time. To reach this exact point in history, with you alive right now, required an unbroken thread that passed through wars, migrations, famines, storms, accidents, illnesses, shifting empires, changing landscapes, misfortunes avoided, fortunes stumbled into, and choices made by people who never knew how profoundly their decisions would ripple outward. If you were to trace your family line backward through the centuries, the path would branch again and again, like a vast and tangled forest. Behind you stands an ever-widening pyramid of individuals, each one essential, each one irreplaceable. Your parents, your grandparents, your great-grandparents, and all the generations before them lived lives full of moments in which things might have turned out differently. A missed meeting, a different journey taken, a moment's hesitation, a sudden illness, a lost harvest, a war that arrived one village away instead of one village closer, a chance encounter that never happened. Change even one of these moments, and your branch of the tree may have ended long before it reached you.
For most of human history, survival was not a guarantee. Childhood was precarious. Harsh winters claimed lives. Diseases arrived suddenly and without remedy. Migration routes carried families into dangerous terrain. Yet your ancestors survived each one of these dangers long enough to continue the line. They grew up, found one another, formed families, and passed on their genes. Imagine how narrow some of those escapes must have been. A storm that nearly took a fishing boat, a fever that almost did not break, a journey through mountains that might have ended in snow, a dry season that threatened crops until the last moment, an argument resolved instead of widened, a friendship, a reunion, a moment of kindness that guided two people together. Your family line is full of these quiet crossings between disaster and survival. Even if the details have been lost to time, every generation had someone who lived through periods of upheaval. There were wars your ancestors endured or narrowly avoided. There were droughts, invasions, and sudden changes in climate. Some were born during peaceful eras. Others arrived during times of turmoil. But all of them continued the line. They found shelter, food, community, or the strength to move on when everything around them changed. Every pairing in your family tree is a story of precise timing. Two people meeting at the exact moment when both were alive, both fertile, both in the right place, both sharing enough common ground that they connected long enough to produce the next generation. This may sound simple, but it is extraordinary. Consider how many opportunities had to align, how many paths had to cross for each ancestor to meet the person who would become part of your lineage. If even one pairing had failed to happen, just one, the entire future leading to you would have vanished. Across the centuries, your ancestors lived through shifting geographies. Some ancestors wandered far across shifting landscapes. Others remained in the same valleys for countless generations. Some journeys were born from necessity, others from hope, and some simply from the quiet pull of curiosity. With every step, with every crossing of a river or following of a trade route, the genetic story of your family changed. A single decision to stay, to leave, to try again could alter everything. A different choice at any moment in that long chain would have created a different future with different descendants, and not you. Even the smallest events shape the path forward. Arriving a little late to a gathering, a brief meeting at a well or a marketplace, a shared harvest field, a borrowed tool, a moment of laughter, a gentle act of help. It is often in these quiet, ordinary moments that human connection begins, soft ripples that eventually lead through time to you. And yet those same moments determined which people paired, which families merged, and which lineages continued. The path to your existence depended on countless interactions that no history book ever recorded. And woven through these connections were periods of loss, because every family carries both survival and sorrow. Some branches ended, some stories closed. Some lines reached their final generation through disease, conflict, or misfortune. But your particular branch endured. It passed through each narrowing point and continued onward, sometimes by a hair's breadth, until it eventually reached the present moment. When you step back and see the scale of the ancestry behind you, the unlikeliness becomes overwhelming. You were the product of millions of moments that could have gone differently. Millions of ancestors whose lives intersected in just the right ways. Millions of decisions, accidents, recoveries, journeys, boundaries crossed, new beginnings, and second chances. The chain did not depend on perfection. It depended on persistence. Think of the centuries when the world felt much larger than it does today. Many of your ancestors lived in villages or small towns, unaware of oceans or continents far beyond their sight. They could not have predicted how their small choices would echo across distant generations. Yet the life you live today is built on their endurance, their movement, their relationships, their survival. The improbability becomes even more striking when you realize that your existence depends on exact combinations of DNA meeting at precise moments. If any of your ancestors had chosen another partner, even one generation back, the genetic outcome would have been completely different. If your grandparents had married different people, you would not be here. If your parents had met at a different time or not met at all, you would not exist in your current form. Perhaps someone else might have been born, but not you. Not this specific person with this mind, this body, this consciousness. The branching of lineages over centuries resembles the roots of a vast ancient tree spreading through soil. Some roots twist upward, some branch sideways. Some split into many directions, and some fade into nothing. Somewhere in that tangled network, one thin root grew in just the right direction, through all the obstacles, storms, and seasons, until it emerged into the present moment, as you. It is strange to think how much chance is built into something that feels as solid as identity. The exact person listening to this now exists because your lineage threaded its way through every narrow opening, every fragile crossing, and every uncertain generation. That thread was stretched, tested, thinned, and nearly broken at many points, but it held. The improbability of your existence does not make life random. It makes it precious. It makes every breath, every thought, every relationship part of a story that survived deserts, ice ages, wars, migrations, extinctions, and the quiet, unrecorded struggles of everyday lives long forgotten. You're not here by simplicity or inevitability. You're here because countless others endured just long enough for the future to continue flowing. The path behind you is extraordinary, and the unlikeliness of this exact person being alive now is one of the most remarkable sections of the entire journey. Perhaps the most personal chapter of all in the long, improbable chain that led to you. Earth's climate has always been a balancing act, a slow and intricate dance between forces that warm the planet and forces that cool it. From the outside, the world might seem steady. Oceans rising and falling with the tides, seasons arriving in familiar rhythms, clouds wandering across the sky in gentle cycles. But beneath that calm lies a network of feedback loops so delicate that even slight changes could, under different circumstances, have pushed the planet into uninhabitable extremes. Life exists because Earth learned to regulate itself, to dampen the chaos, and keep temperatures within a narrow window where water can remain liquid and living systems can flourish. One of the most important stabilizing forces is the carbon cycle. Carbon dioxide is a heat-trapping gas essential for maintaining a temperature warm enough for life. Without it, Earth would be a frozen sphere of ice. With too much of it, however, the planet could become dangerously hot, shifting toward a runaway greenhouse state where temperatures rise uncontrollably. Finding the middle ground required Earth to develop natural mechanisms that regulate how much carbon remains in the air. These mechanisms are slow, ancient, and remarkably effective on geological timescales. When atmospheric carbon dioxide increases, the planet warms slightly. This warmth speeds up weathering, the process in which rainwater reacts with rocks on land.
Those reactions pull carbon dioxide from the air, locking it into minerals that are eventually carried by rivers into the sea. There, over millions of years, the carbon becomes trapped in sediments. In this way, the planet slowly draws down excess carbon dioxide, cooling itself. When carbon dioxide levels fall too low, the planet cools. Weathering slows. Volcanoes continue releasing small amounts of carbon dioxide into the air. Over long stretches of time, this gradually increases atmospheric levels again, warming the climate. It is a self-correcting system, like a vast planetary thermostat. But the carbon cycle is not the only feedback loop quietly maintaining balance. Ice, for example, plays a powerful role. Ice reflects sunlight far more effectively than land or water. When ice sheets grow, they bounce more solar energy back into space, cooling the planet further. This can lead to more ice forming, a reinforcing cycle.
If this process accelerates too quickly, the planet risks slipping into a deep freeze. There were times in Earth's past when ice expanded dramatically, potentially covering the entire surface in white. These episodes, sometimes called snowball states, pushed the planet to its limits. Yet even then, another feedback loop stepped in. When Earth is covered in ice, weathering slows almost to nothing. But volcanoes do not stop. Carbon dioxide from deep within the planet continues to rise through volcanic eruptions, accumulating in the atmosphere because there is no weathering to draw it back down. Over millions of years, this buildup causes the planet to warm. Eventually, the ice begins to melt. Darker surfaces become exposed. They absorb more sunlight. The planet warms faster. Slowly, Earth escapes its frozen state. The balance returns. Oceans contribute to this delicate equilibrium as well.
Water has a remarkable ability to store heat, absorbing excess energy and releasing it slowly over time. This moderates temperature swings between seasons and even between day and night. Without the oceans acting as giant heat reservoirs, Earth's climate would be far more erratic. The oceans also absorb carbon dioxide directly from the air. When the water is cool, it takes in more carbon dioxide. When it warms, it releases some back into the atmosphere. This natural exchange helps stabilize global temperatures over long periods. Currents within the oceans distribute heat around the world. Warm water flows from the equator toward the poles. Cold water sinks and returns along deep pathways. These currents create a global conveyor belt that moves heat, nutrients, and carbon between regions. If these currents stopped or changed drastically, climate patterns could shift in unpredictable ways. In Earth's history, there were moments when major currents slowed or redirected. And each time, the planet's temperature and weather patterns responded dramatically. Yet, the system always returned to a state that allowed life to continue. The atmosphere participates in this balancing act too. Clouds can cool the planet by reflecting sunlight, yet they can also warm it by trapping heat near the surface. The exact effect depends on cloud height, thickness, and distribution. These properties shift constantly, influenced by temperature, humidity, and the movement of the air. It is a dynamic, ever-changing system, full of small counterweights that keep the climate from running off in one direction. And then there is the role of life itself. Plants absorb carbon dioxide through photosynthesis, storing it in their tissues. When they die, Some of that carbon becomes trapped in soils or sediments. Marine organisms build shells from carbon compounds, which settle to the ocean floor when they die. Over millions of years, layers of these shells build thick deposits of limestone. This biological activity forms another feedback loop. Life stabilizes the climate that allows life to exist. It is a quiet cooperation between biology and geology, each depending on the other. The fine balance of Earth's climate becomes even clearer when imagining the alternatives. A slight increase in the greenhouse effect could have pushed Earth into a Venus-like state, with thick clouds of gas trapping heat so effectively that temperatures rise far beyond anything sustainable. A slight decrease could have plunged the planet into a permanent ice age. Both scenarios are entirely possible on worlds that lack the feedback loops Earth possesses. Other planets in our solar system show how easily climates can slip into extremes. Mars lost most of its atmosphere long ago, becoming cold and barren. Venus experienced a runaway greenhouse effect that turned it into a scorching desert. Earth avoided these fates through a mix of fortunate starting conditions and self-correcting systems that developed over time. The presence of liquid water, for instance, allowed the carbon cycle to function effectively. The formation of continents created land surfaces that could be weathered. The moon stabilized Earth's tilt, preventing severe swings in climate. Life evolved mechanisms that contributed to long-term carbon storage. The planet became a web of interacting systems, each influencing the others in subtle but critical ways. These feedback loops did not emerge with intention or design. They developed because Earth's physical and chemical properties interact in ways that naturally counteract extreme changes. The planet cools when it becomes too hot. It warms when it becomes too cold. But this does not happen quickly. These stabilizing forces operate over thousands, millions, or even tens of millions of years. They do not prevent short-term changes, but they do protect the planet from long-term catastrophe. Even so, Earth's climate has never been perfectly steady. There were ice ages, warm periods, oscillations, and disruptions. But compared to the extremes that could have occurred, these variations were modest enough to allow life not only to survive, but to evolve in complexity. Without these stabilizing systems, the story of life would have been much shorter and simpler. There would have been no forests, no animals, no humans. The delicate balance Earth maintains is not one of stillness, but of constant adjustment. It is a dynamic equilibrium, a shifting interplay of forces that together keep the planet hospitable. Each component depends on the others. Oceans influence the atmosphere. Ice shapes temperature. Volcanic gases guide the carbon cycle. And life quietly influences almost everything in return. On Earth, when one system drifts too far in one direction, another slowly rises to meet it, gently pulling the world back into balance. It's a fragile choreography, easy to overlook when the day feels peaceful. A warm breeze, a soft rain, a gentle winter, a spring that arrives right on time. These simple moments hide a profound truth. Beneath the calm surface lies one of the most elegant balancing acts in the universe. A planet constantly adjusting itself, breath by breath, to remain within the narrow window where life can bloom. And from that delicate stability, kept steady over billions of years, came the conditions for life to grow, to change, to multiply, and ultimately to become aware of itself. The improbable path to you required more than the right star and the right distance. It required a planet capable of protecting itself from extremes. A world that could endure ice, fire, impacts, and time. A world that could stay balanced long enough for consciousness to emerge. Earth became that world. And through its quiet feedbacks, its self-correcting cycles, and its improbable steadiness, it kept the long story of life moving forward, carrying every generation, every species, and every fragile moment toward the present day, and toward you. Human history is often told as if it were a steady march from simple beginnings toward modern civilization. But the real path was narrow, fragile, and shaped by countless moments of chance. Behind every invention, every cultural shift, every expansion of knowledge, there were turning points where things might easily have gone the other way. Entire ideas were nearly lost, languages faded, empires rose and collapsed, migrations redirected the flow of history. And yet, through all these twists, threads of culture survived long enough to shape the modern world, and eventually shape the life of the person listening now. Cultural evolution is very different from biological evolution, though both share a dependence on what manages to endure. A clever idea is not guaranteed to survive simply because it is useful. It has to be shared. It has to be written down or repeated, taught or remembered. It has to find a community that values it. Many ideas vanish before they spread. Others survive because one person happened to tell another at exactly the right moment, or because a group carried a memory across a landscape while traveling, or because a fragment of writing managed to escape a fire. Civilization is built not on a smooth accumulation of knowledge, but on knowledge that managed to persist through fragile and unpredictable circumstances. When their humans began sharing stories, techniques, and tools, culture became a force that could shape the future. People learned from one another, refining the ways they hunted, gathered food, crafted tools, and organized their communities. These cultural exchanges were small at first. Simple ways of knapping stone, techniques for starting fires, paths through terrain, herbal remedies. But every exchange widened what a group could accomplish. Culture allowed information to cross generations instead of being reinvented from scratch every time a child grew up. It created a sense of continuity. But continuity was never guaranteed. Many early cultures lived in regions vulnerable to droughts, floods, storms, or migration pressures. A single natural disaster could scatter a community, taking its knowledge with it. Stories were fragile. Memories were fragile. Traditions could vanish if even one generation failed to pass them on. The fact that early tool-making techniques, symbolic art, and forms of communication survived long enough to spread across continents is remarkable. It depended on stable groups, cooperative behavior, and long periods of relative safety. As humans formed larger settlements, the stakes grew higher. Agriculture required knowledge of seeds, seasons, irrigation, and storage. The earliest farmers did not simply plant crops and hope for the best. They relied on accumulated wisdom from generations who had observed the land closely. If that knowledge had been disrupted, if a drought or flood had scattered the early farming communities, agriculture might never have taken hold in the ways it eventually did. Civilization emerged from small cultural successes that managed to persist despite constant threats. Writing is one of the clearest examples of cultural fragility. The ability to record information transformed what humans could preserve.
But early writing systems were rare and vulnerable. Clay tablets cracked, papyrus decayed, libraries burned, entire archives vanished into the dust. There were moments in history when vast collections of knowledge, philosophy, medicine, mathematics, and literature were nearly erased. The fact that any text from the ancient world survived long enough to influence later cultures came down to chance as much as intention. A single scroll stored in a distant monastery, a copy made by a careful scribe on a quiet night, a trader carrying a book across unfamiliar lands, even major inventions balanced on threads of unpredictability. Consider the discovery of metalworking. It required not only the recognition that certain rocks melted, but the realization that they could be shaped and hardened into tools. If early experiments with furnaces had been slightly less successful, or if knowledge had been lost after a village conflict, metalworking might have been delayed by centuries. That delay would have reshaped everything from trade to warfare to agriculture. Chance migrations played an enormous role as well. When groups of people left their homelands, sometimes by choice, sometimes by necessity, they carried their traditions with them. Some brought seeds, spreading crops across continents. Others brought language, blending dialects into new forms. Some introduced technologies to places that had never seen them before. These migrations often occurred because of unpredictable changes, a shift in rainfall patterns, the movement of animals, a sudden cold period, or tensions with neighboring groups. Each migration altered the flow of cultural exchange. A different set of migrations could have produced a very different world. History is dotted with small turning points that reshaped entire civilizations. A single battle avoided, a single alliance forged, a single leader deciding to welcome travelers rather than repel them, a single invention adopted quickly instead of slowly. Behind every major shift were thousands of small decisions made by individuals who never imagined their choices would influence the future. A fisher choosing a new route along the coast, a farmer trying a different seed, herbalist trusting an unusual mixture and discovering healing property. These moments, unnoticed at the time, carried culture forward. There were also moments when history nearly erased key ideas. Technology such as the compass, printing, advanced mathematics, and early forms of navigation all moved through vulnerable channels. If the people carrying them had perished during a storm or abandoned their journeys due to illness, those innovations might have taken centuries longer to spread. Even the concept of scientific inquiry, observing the world, asking questions, testing ideas, survived through periods when it could easily have vanished. Military conflicts burned libraries. Changing regimes discouraged scholarship. Epidemics disrupted social structures. Yet enough people continued to study, to teach, to learn, and to preserve fragments of knowledge so they could be rebuilt later. Looking across the sweep of history, one can see how cultural threads weave together in ways that defy prediction. The rise of mathematics in one region influenced engineering in another. Navigational techniques developed by one culture unlocked long-distance exploration for another. Medical practices, astronomy, architecture, philosophy, all of these fields grew because ideas traveled from person to person across generations and landscapes. If certain routes had never opened, if certain people had never met, the world today might be unrecognizable. Some of the most profound turning points in history hinged on what seemed like minor events. A king's decision to fund a voyage, a teacher taking on a curious student, an artisan discovering a new firing technique for pottery, a scribe copying a nearly forgotten manuscript,
a merchant bringing seeds home from a foreign land. Every one of these actions set off ripples, and while many of those ripples faded quickly, some grew into waves that influenced the development of entire civilizations. The thin path of human history becomes even more striking when you consider how easily cultures can fragment or disappear. Countless ancient peoples left behind only faint traces. Tools buried in sediment, symbols carved in stone, fragments of pottery decorated with patterns whose meanings are lost. Their ideas may have been brilliant, their societies rich and complex, yet their knowledge did not survive the centuries. The existence of modern cultural traditions depends on a long chain of preservation that succeeded where many others failed. What survives is not always what is most valuable. Often, it is simply what was copied, what was portable, what found its way into stable communities, what was lucky enough to avoid destruction. Culture evolves not because it is perfect, but because it is carried forward by people doing their best to hold on to what they believe matters. Each generation chooses what to keep, what to change, and what to forget. And through this long chain of choices, you now live in a world shaped by the knowledge that survived a series of narrow escapes. The tools you use, the languages you speak, the stories you know, the technology that powers your daily life, all of it descended from ideas that passed through centuries of uncertainty. Every invention could have been lost. Every discovery could have faded. Every tradition could have dissolved. The improbable path to you does not end with biology. It continues through culture, through the thin, winding passage of human history, where ideas flickered like small lights in the dark, carried from person to person until they reached the present. Your world exists because enough of those lights stayed lit long enough to illuminate the road ahead. You are here in this exact moment because an entire universe spent billions of years arranging itself into the one configuration that could lead to you. Not just a human being in general, not just a member of your family, but you, the specific person listening to this right now with your thoughts, memories, and private inner world. Everything that came before, from the birth of the first stars to the choices made by your distant ancestors, narrowed step by step until the long cosmic journey arrived at this single point in time. Your personal ancestry is a story deeper than you might ever see written out, because it stretches far beyond family trees and historical records. It reaches back through generations that lived in small villages, bustling cities, migrating bands, quiet farms, and places you may never have heard of. Each one of those people woke up in their world, lived a life filled with ordinary moments and extraordinary challenges, and passed on the fragile thread of existence that eventually arrived here, connecting them to you across centuries and continents. If you could see that thread branching endlessly through time, it would look like a vast map of converging paths shaped not only by big events, but by countless small decisions. Decisions that, at the time, felt simple or unimportant. Someone choosing to take shelter from a storm. Someone deciding to join a festival on a particular night instead of staying home. Someone crossing a river rather than stopping on the near side. Someone looking up at the right moment, meeting someone else's eyes, forming a connection that would change everything that followed. Some decisions were thoughtful,
Others were instinctive. Many were barely noticed.
Yet every small turn kept your lineage moving forward, guiding it through all the narrow openings that history allowed. You exist because long ago, one ancestor decided to travel instead of staying put, shifting your family line in a completely new direction. You exist because another ancestor survived an illness that might easily have taken them. You exist because two people met under circumstances that seem, in hindsight, astonishingly specific. Even if one moment along the chain had gone differently, if someone had left home one day earlier or one day later, the entire path that leads to you might have changed forever. Every person has this intricate history behind them. But what makes your existence even more unlikely is that you are alive now in this era of all eras. Human history spans only a tiny fraction of Earth's timeline, and your lifetime occupies an even smaller fragment of that. For thousands of generations, people lived and died without ever glimpsing the world.
They experience different climates, different technologies, different societies, different understandings of the universe. Out of all those periods, times of wandering, farming, building and rebuilding, you happen to arrive in this one. To be alive during this era means you were born into a moment when global communication exists, when knowledge is preserved and shared instantly, when medicine can treat illnesses that once would have ended family lines, when cultures interconnect on a scale unimaginable to past generations. You were born at a time when the universe is understood in ways that your distant ancestors could not have imagined. You were born in a moment when climate, technology, culture, and biology aligned in such a way that your life could unfold with the unique shape it has taken. From another angle, this moment is not inevitable. It is the product of countless fragile conditions holding steady. The right people meeting, the right families forming, the right ancestors making it through wars, migrations, environmental shifts, famines, and periods of peace. The right conditions holding on Earth for civilization to develop. The right environmental stability for humans to thrive. The right inventions surviving long enough to create the world you live in now. If even one major thread had broken, the entire future would have shifted. Think about the unique set of circumstances that allowed your life specifically. The place you were born, the people who raised you, the communities you moved through, the friendships that shaped you, the opportunities that appeared just as you were ready for them, the hardships that challenged you but did not break you. Your journey is full of these subtle turning points, moments when things could have gone differently but didn't. Even your own internal world is a product of uniquely unlikely conditions. Your personality is shaped by an intricate mixture of genetics, experiences, timing, environment, and the small personal choices you've made across your life. Your memories formed in one particular order. Your relationships grew from specific moments of connection. Your ideas emerge from conversations, observations, and quiet reflections that no one else has lived through in quite the same way. Another version of the world, even one only slightly altered, might never have produced someone exactly like you. The more you follow the chain backwards, the narrower it becomes. You can trace it from your parents to their parents, and then to theirs as it weaves back through time, through ages of exploration, settlement, survival, and change.
Behind them stand ancestors who lived through ice ages, famines, migrations, cultural turning points, wars, discoveries, and long stretches of quiet in which nothing notable happened. But life continued nonetheless. Behind them stand countless generations whose names you may never know, but whose existence was essential to yours. They lived in environments that tested them, in societies that changed around them, in climates that shifted, sometimes gently and sometimes brutally. Yet each one stayed alive long enough to take the next step in a chain that could so easily have ended at any point. Pull back even further, and the chain grows longer still, tracing not only human ancestry, but the entire evolutionary story that preceded it. The earliest mammals hiding from predators, ancient primates navigating forests, early humans learning to cooperate, migrate, adapt, and survive. Before them, simple organisms, survivors mass extinctions. Before them, the first cells enduring a chaotic young Earth. Before them, the chemistry that stirred in ancient oceans. Before that, the planet forming in a narrow zone around a rare type of star. And further still, the stars that exploded to create the heavy elements your body uses. And even further back, the universe beginning in a way that allowed matter, complexity, and life to emerge at all. It all narrows step by step down a long corridor of improbable events until the entire journey arrives here, at a person living on a blue world, thinking, feeling, listening, breathing. Your existence is not a simple outcome. It is a convergence, a meeting point for the ancient and the recent, the cosmic and the personal, the vast and the intimate. The universe spent 13 billion years unfolding in such a way that a particular ancestry could form, that a particular chain of survival could persist, that a particular set of choices could be made, that a particular life could emerge. And here you are, in this exact moment, a single, irreplaceable outcome of an unimaginably long and fragile journey carried forward by stars, planets, oceans, ancestors, ideas, and chance. The improbable path to you has been narrowing for billions of years, and you are the brief, shining point where all those threads meet. You're here in this exact moment because an entire universe spent billions of years arranging itself into the one configuration that could lead to you. Not just a human being in general, not just a member of your family, but you, the specific person listening to this right now, with your thoughts, memories, and private inner world. Everything that came before, from the birth of the first stars to the choices made by your distant ancestors, narrowed step by step until the long cosmic journey arrived at this single point in time. Your personal ancestry is a story deeper than you might ever see written out, because it stretches far beyond family trees and historical records. It reaches back through generations that lived in small villages, bustling cities, migrating bands, quiet farms, and places you may never have heard of. Each one of those people woke up in their world, lived a life filled with ordinary moments and extraordinary challenges, and passed on the fragile thread of existence that eventually arrived here, connecting them to you across centuries and continents. If you could see that thread branching endlessly through time, it would look like a vast map of converging paths. Paths shaped not only by big events, but by countless small decisions. Decisions that, at the time, felt simple or unimportant. Someone choosing to take shelter from a storm. someone deciding to join a festival on a particular night instead of staying home, someone crossing a river rather than stopping on the near side, someone looking up at the right moment, meeting someone else's eyes, forming a connection that would change everything that followed. Some decisions were thoughtful, others were instinctive, many were barely noticed. Yet every small turn kept your lineage moving forward, guiding it through all the narrow openings that history allowed. You exist because long ago, one ancestor decided to travel instead of staying put, shifting your family line in a completely new direction. You exist because another ancestor survived an illness that might easily have taken them. You exist because two people met under circumstances that seem in hindsight astonishingly specific. Even if one moment along the chain had gone differently, if someone had left home one day earlier or one day later, the entire path that leads to you might have changed forever. Every person has this intricate history behind them. But what makes your existence even more unlikely is that you are alive now in this era of all eras. Human history spans only a tiny fraction of Earth's timeline, and your lifetime occupies an even smaller fragment of that. For thousands of generations, people lived and died without ever glimpsing the world you know. They experienced different climates, different technologies, different societies, different understandings of the universe. Out of all those periods, times of wandering, farming, building and rebuilding, you happen to arrive in this one. To be alive during this era means you are born into a moment when global communication exists. When knowledge is preserved and shared instantly, when medicine can treat illnesses that once would have ended family lines, when cultures interconnect on a scale unimaginable to past generations. You are born at a time when the universe is understood in ways that your distant ancestors could not have imagined. You were born in a moment when climate, technology, culture, and biology aligned in such a way that your life could unfold with the unique shape it has taken. From another angle, this moment is not inevitable. It is the product of countless fragile conditions holding steady. The right people meeting, the right families forming, the right ancestors making it through wars, migrations, environmental shifts, famines, and periods of peace. The right conditions holding on Earth for civilization to develop. The right environmental stability for humans to thrive. The right inventions surviving long enough to create the world you live in now. If even one major thread had broken, the entire future would have shifted. Think about the unique set of circumstances that allowed your life specifically. The place you were born, the people who raised you, the communities you moved through, the friendships that shaped you, the opportunities that appeared just as you were ready for them, the hardships that challenged you but did not break you. Your journey is full of these subtle turning points, moments when things could have gone differently but didn't. Even your own internal world is a product of uniquely unlikely conditions. Your personality is shaped by an intricate mixture of genetics, experiences, timing, environment, and the small personal choices you've made across your life. Your memories formed in one particular order. Your relationships grew from specific moments of connection. Your ideas emerged from conversations, observations, and quiet reflections that no one else has lived through in quite the same way. Another version of the world, even one only slightly altered, might never have produced someone exactly like you. The more you follow the chain backwards, the narrower it becomes. You can trace it from your parents to their parents, and then to theirs, as it weaves back through time, through ages of exploration, settlement, survival, and change. Behind them stand ancestors who lived through ice ages, famines, migrations, cultural turning points, wars, discoveries, and long stretches of quiet in which nothing notable happened, but life continued nonetheless. Behind them stand countless generations whose names you may never know, but whose existence was essential to yours. They lived in environments that tested them, in societies that changed around them, in climates that shifted, sometimes gently and sometimes brutally. Yet each one stayed alive long enough to take the next step in a chain that could so easily have ended at any point. Pull back even further, and the chain grows longer still, tracing not only human ancestry, but the entire evolutionary story that preceded it. The earliest mammals hiding from predators, ancient primates navigating forests, early humans learning to cooperate, migrate, adapt, and survive. Before them, simple organisms surviving mass extinctions. Before them, the first cells enduring a chaotic young Earth. Before them, the chemistry that stirred in ancient oceans. Before that, the planet forming in a narrow zone around a rare type of star. And further still, the stars that exploded to create the heavy elements your body uses. And even further back, the universe beginning in a way that allowed matter, complexity, and life to emerge at all. It all narrows step by step down a long corridor of improbable events until the entire journey arrives here, at a person living on a blue world, thinking, feeling, listening, breathing. Your existence is not a simple outcome. It is a convergence, a meeting point for the ancient and the recent, the cosmic and the personal, the vast and the intimate. The universe spent 13 billion years unfolding in such a way that a particular ancestry could form, that a particular chain of survival could persist, that a particular set of choices could be made, that a particular life could emerge. And here you are in this exact moment. A single irreplaceable outcome of an unimaginably long and fragile journey, carried forward by stars, planets, oceans, ancestors, ideas, and chance. The improbable path to you has been narrowing for billions of years, and you are the brief, shining point where all those threads meet.